Hello guys, we're gonna get started now with Rev 3. Next slide, please. All right, so first some announcements. We have CyberTracker applications are open. They're still open. They've been open for a while. I did this program last year. It was a lot of fun. They fly you out for a week to Des Moines, Iowa, and you do a lot of cool stuff, which you won't be able to talk about later. So if you're interested, you should definitely apply. It's even if you're a freshman and like no background experience, that's fine. There's still a good chance you'll get in. Very relaxed program. Not a lot of prerequisites needed. ICSP, that's the scholarship program, where the government will pay you money to go to school, and then you have to work for them later. That's the gist of it. So sign up if you're, go to their informational meeting if you're interested in that. And lastly, we have SAIL, which George is here.
Right on time.
Yes.
Yeah. Hello. CS SAIL is the CS department's, promotional event for prospective high school students. Right now, we are asking for teachers. Basically, that means you give a little about an hour-long seminar. You do it with a group of friends. You get free food, free swag, and you get to kind of promote whatever it is you want to teach to some high school students. I highly encourage you. The form is open until tomorrow. The link is in the slides. Also on SIGPwny Discord, if you need a link or QR code, you can just ask me after the meeting.
All right, thank you, George. Let's this is the meeting flag. So if you guys want to put this into ctf.sigpwny.com. Yeah, I came up with this flag at like last night at like 1 a.m. So did you make them? Oh no, I found this meme. I was just like meme about virtual machines in Google Images. This is like one of the first hits. Yeah, kind of ironic because we're not going to be talking much about containers, but yeah, it's a meme. Yeah, and these slides will be on Discord, so you can find the flag there also. All right, so here's the topic list for today. We're going to be covering a lot of stuff, but don't get overwhelmed. There's going to be examples and some challenges for each one. So just a brief overview. I'm going to talk about what a virtual machine is and how you might go about reversing it. And then instrumentation tools, side channel attacks, instruction counting, and the like. And then lastly, memoization, which is a way to speed up programs that can help tremendously when reversing certain pieces of code. All right, virtual machines. What is a VM? That's a great question. The answer's on the slide, but I'll just paraphrase that. So a virtual machine has a bunch of instructions that basically emulate a computer. It's a virtual machine. Machine as in it is a computer, but virtual because it runs on your computer, not on real hardware. So there's some pretty famous ones like QEMU. I'm sure you've all heard of it, probably have used it for classes. It can run a variety of instruction sets, such as the infamous x86. But for CTF challenges, we're going to be talking more about obscure instruction sets and obscure VMs that are used to obfuscate code, to hide how it works. This is an additional layer of abstraction that can make it a lot harder for you to reverse. But as you'll see in a moment, it doesn't need to be that difficult if you have the right tools. So there's two main types of VMs, a stack-based and a register-based. Most virtual machines you see in real life will be a mix of the two. So a stack-based VM uses the stack to push stuff, and then the operations work on the stack itself. This will be the type of VM that's the VMware challenges on ctf.sigpwny.com. You can just take a peek at that now if you're bored, but the VMs for that will be based on a stack-based VM. Okay. Next slide. And the registers, you have registers, you can shift data around between the registers, and all the operations work on the registers. Usually for register-based VM, you still need some sort of separate space for data because it's hard to do stuff with just registers, even if you have like 1,000 of them. Okay, Next. So how do we go about reverse engineering these? So one of the crucial things is to generate a control flow graph, which is a graph of the control flow of the instruction pointer of what instructions are being executed in what case. And then using tools like disassemblers to generate that, and then debuggers to step through and verify that control flow graph is what you think it is. So a lot of this tooling will be available for commonly seen VMs, but for a lot of CTF challenges, you're gonna have to build your own tools. Now, for the purposes of today, I've provided you a disassembler for the VM challenges on the SIGPwny PFD. So you won't have to write the disassembler, but that's just like a demonstration. And it's something that you would need to do for like a real challenge. Okay. So what is a control flow graph? Again, it's a graph of the control flow. If each node on here is a basic block, the basic block has a single entry point and a single exit point. Think of it as like a block in your code, a block surrounded by the curly braces, if you're familiar with C or Java and the like. And then the blocks can have multiple exit points, arrows going out of them if they're like conditional statements, like if they're if state something if statement, and then usually an arrow going back. I put back in quotation marks because sometimes it's hard to determine which nodes are going back, but an edge going back usually indicates a loop. So these are some common things to look for. And then one more thing is this control flow graph here has multiple exits, and a lot of the ones that we'll see today may have only one exit because the program eventually the instruction pointer will all end up at the same place, which is the exit pointer, or the exit function. And it's up to you to determine which of these nodes sort of correspond to a good output and a bad output. Okay. So yeah, these are some good questions to ask once you have a CFG. You know, what is the win condition? What nodes are good? What nodes are bad? How do we get there? Think of the control flow graph as a map for the program when you don't have the source code, because a lot of times with VMs, it's just a bunch of instructions, right? When you don't have the source code, this is the next best thing. And Ghidra isn't going to help you much because it can't decompile a VM it's never seen before. Okay, next slide. Yeah, so the question is why Ghidra doesn't work with this. So there's the main issue is that there's multiple layers of abstraction. So the Ghidra will typically be able to decompile the original VM. You know, today it's going to be written in C, so it's going to do a good job of decompiling that. But once it decompiles that, you'll see that the VM just runs instructions. There's not much in terms of code. So you need to go one abstraction level higher and look at the actual instructions it's running. And Ghidra just, you know, doesn't have anything built in to decompile that. Now you could write your own decompiler if you knew how the VM instructions were compiled. But that's significant work and sort of beyond the scope of this presentation. So, any other questions? That's a good question. Okay, we'll move on then. Some tips and tricks. This is sort of pretty miscellaneous. I put magic numbers on there because this really tripped us up at Seesaw. There's this magic number which we didn't realize until it was too late. But this, if you just Google like random numbers that you see in the binary that look like they're not like all zeros or all ones, you know, this looks like a pretty suspect number. If you Google this number, for example, it's the golden ratio, which is used in a particular cipher algorithm called the T algorithm. Yeah, other tips, verifying assumptions, and then brute force, which I will talk about on the next slide. Okay, so a lot of the times you don't need to even think about how to reverse the VM. You can just brute force it because, you know, maybe it was poorly written, or I don't know, maybe that was the intended solution. Most notably, when you can brute force any program really, when the inputs sort of break early. This sense of once it encounters something incorrect, it will end the program early, and there's some way for you to determine that the program has been ended early. So such as look at this example here, which is sort of written in a pseudocode. You can imagine this as C, or maybe some C-like language compiled down to instructions for VM or something like that. You can see here on the if line. So if it finds a character that's wrong, it will immediately return. So this means that you can just go through and try every character for the 0th position and every character for the 1st, 2nd, 3rd position, so on and so forth. And then you'll get the full flag. But this only works some of the time though. A lot of times it'll be all you need. So here, let's see an example. One of the common tools that you can use for doing brute forcing is GDB Python. It's Python scripting within GDB. This is example the script. If you the next different parts of the script. Down up there, the top arrow, we set a breakpoint where the program is doing the check. So if we go back to the previous here, previous slide, you can think of the breakpoint as being set on the if line. So we're setting a breakpoint every loop iteration essentially. And then we once we hit the breakpoint, we see if the character, or sorry, we set the breakpoint at the break statement, not once per loop, once per program run. So you see the break line. Oh, my bad. Once we hit there, we see if the input that we've given it was correct. Using, GDB has this parse and eval, which is lets you get some sort of value from GDB. So if you're familiar with GDB, the $ is a register. So this bottom left arrow, we're just getting the register value in REX. In this case, I'm assuming that REX stores how many characters of the input string was correct, but that's going to change depending on your program. Yes.
This is a little unrelated, but scripts aren't compiled, correct?
No, so scripts are interpreted. To run this script, you would use GDB with, I think, -X or something. You can look that up, or -X. And GDB will run this script, and this script will tell GDB how to do certain things. So if you look at the top left part, GDB.execute, that like sets the file, sets the breakpoint. These are all commands that you would normally type into GDB, but instead Python is sort of doing this typing for you. That's the power of scripting. So yeah, and then we're trying every character. The right arrow on the right hand side, we're trying every character for every position. This is, if you think about this is actually not a lot of tries that we have to do. So if the flag was like 40 long and we have to do like say 40 different characters, that's only 1600 tries, which is a lot better than brute forcing every like 40 to the 40 possible characters. So it's very doable for a lot of programs. All right, next slide. So yeah, well, the topics I've covered here, if you go to cdf.sigpwny.com, the VMware 0 to 2 series will cover a lot of these techniques. I will be going through a walkthrough of VMware 0 at the end of the meeting. So yeah, so now we'll go on to instrumentation. Okay, computers go purr. Some background on instrumentation. Instrumentation is a dynamic analysis tool. That means it runs when the program is running. So Ghidra is probably the most popular static analysis tool because it doesn't run the program. You're just looking at the program's assembly in sort of a different way by decompiling it. But with instrumentation, you are running the tool and you're doing stuff as it runs. So what are you doing? What you're doing is, well, okay, sorry. So first, let's do some motivation. So what if you wanted to do these things, like print every string compare call? Would you set a breakpoint in GDB and then maybe use GDB Python to print every time it breaks? That could be very slow if there's a lot of string compares. What do you want to call count the number of function calls. Again, this could be very slow if you're going to do it manually, just setting a breakpoint GDB and type continue counting how many times. So there's ways to automate this. Next slide. And can you just skip the slide for now? The main way is to use PinTool. And PinTool is an instrumentation framework that essentially breaks down the binary into different sections called basic blocks, which I explained earlier. They have one entry point, one exit point, and they let you add custom code to those basic blocks. So this is a diagram of like the pin architecture. At the top, it fetches in code from the process and it rewrites the code, adding in the instrumentation that you've given it on the right-hand side, the DBI tool. So in here, we're registering like a callback, and the callback can do anything. It can change register values. It can read them, print them, do a lot of things. Now, the power of something like this is that it will recompile, sort of using this JIT compiler, recompile your code so that it fuses with the existing binary, and it's much faster than using something like GDB. Because GDB will use, at least on Linux, it'll use ptrace to hook into the binary to set breakpoints, and that can be very slow if you do set a lot of breakpoints. So, PinTool, can you go back to the previous slide? Yeah, so control flow recovery, right? That's the basic blocks that we're doing. Yeah, next slide. We'll just skip the slide in the interest of time. So some use cases of instrumentation, as I've talked about earlier, instruction counting, like counting the number of function calls or just counting the number of instructions in total. This can be done very quickly and reliably. So if you think about the previous example of brute forcing, one way you can brute force is count how many instructions are executed for a certain input, and then do that repeatedly until you get some input that gives you slightly more instructions. So you can also trace a VM's execution. I'll give an example of that in a moment. And you can trace a lot of things like memory or syscalls. So yeah, a lot of possibilities. And then as for some tools, the one I've been talking about is Intel's PinTool. It's very fast. It works for x86 and ARM binaries. Yeah, despite the name Intel, it also works for ARM, which is pretty amazing. GDB Python is slower but easier to learn. And then there's also one called Dynamo RIO. I believe there's an old SIGPwny slideshow about using Dynamo RIO. So if you want to go to the SIGPwny website, you can look that up if you're interested. That's a little bit harder to use than Pin, but it's open source. So, okay, now we'll go through an example. I'll talk a little bit about obfuscated, which is a challenge I did in UIUCTF 2021. This is a VM reversing challenge written by Nathan, who's right here. Thank you for this challenge, by the way. It is a blast to solve, but very tough. One of the big issues it was hard is because it's such a long VM. The examples I've given you today are on the SIGPwny CTFD are going to be very short, but this was just a massive program. So there was no way to go through every instruction manually. So brief overview of what I did is I used PinTool to dump the instructions that were being executed. So not just the raw instructions, but I sort of figured out what each individual instruction of the VM was. And I printed each of those as the process ran. I analyzed the control flow graph, and then I looked for patterns, and I realized that there were a lot of common code snippets, sort of short pieces of VM instructions that all did like a particular thing. And then I realized that this was compiled from something called ELVM, which is similar to LLVM. Well, actually not that similar, but it's a compiler from C to this intermediate representation that's very easy to write VM backends for. So I I assume that this is what Nathan used to write this obfuscated challenge. And then once I decompiled it to this ELVM intermediate representation, it became a lot easier because there's less code to look at. And the control flow graph, it's also a lot simpler, as we'll see in a second. And then after that, I just stepped through the program and then looked for where it was comparing the inputs and how I could recover the flag from that. So yeah, the first thing I did is I printed the instructions. So on the left-hand side here, the left two most columns are like the original instructions, sort of each. In the second column on the left, each number represents a single VM. You can think of it as a single VM instruction. So at least that corresponds to the line on the right. And here the instructions are prop chain return-oriented programming segments. So it starts with some sort of x86 instruction and ends with ret. So for those of you who are familiar with ROP, you can see that this is just one long ROP chain, just quite cursed. And then next, yeah. So from there, I found this the structure in the code, and then I decompiled that to this is the ELVM representation. If you go back to the previous slide, you can see there are some repeating segments. Can anyone spot a repeating segment? Or sort of repeating. So there's the last four lines. The last four lines are sort of duplicates, or the last two lines are duplicate of the two lines above that. And then the first of roughly 5-6-ish lines are all very similar in structure to the next 5-6-ish lines. So that's how I sort of figured out this was like a ELVM thing. Next slide. Yeah, we'll skip that. So this is the original control flow graph. This is a map of the program, but it's very hard to look at. It's very hard to understand what's going on because there's so much stuff. But this is from the ROP chain, which is had a lot of extraneous code. And you can see a lot of them. So each dot here represents a basic block, and then the arrow represents an edge. Although my basic block detection did not work very well. So as you can see, some of them here have only have one outgoing edge, and they always go to the next one, which those could probably be consolidated. If you go to the next slide, so this is the control flow graph after I decompiled to ELVM. You can see this is much simpler to look at, and this gives you a sense of what the program is doing. I know these are just numbers, but you can see there's like sort of two loops. So the colors here, red means that a branch is taken more often, and then black means a black edge just means it's taken less often. So you can see there's like this sort of smallish loop in the middle, and then a biggish loop on the bottom left-hand side that corresponds to different parts of the program. I believe the bottom left loop is the thing that checks the flag. But yeah, so this was obfuscated. As you can see, the control flow graph sort of helped me understand the overall structure of the program. Yes, question?
To generate this control flow graph by throwing the ELVM IR into a static analysis tool like GDB, or is there a specific tool for generating these control flow graphs?
So the question is, how did I generate these control flow graphs? So I did not use GDB. I used just the GraphViz library in Python. So I printed the instruction pointer as it executed, and then recovered the basic blocks from that. I just looked at the instruction pointers and then checked if it was like consecutive, basically. That's a very crude method of determining basic blocks. And then from there, I put that into this GraphViz library that generated this particular graph. So all I had to do for that is just specify what the nodes were and where the edges were. Yeah, cool. Next slide. Yeah, the big idea here is just working your way up the abstraction chain because let's face it, nobody's going to write 4 megabytes of assembly. So even if the binary is very large or you see a lot of code, there's likely not really a lot of code. And there's ways to find the patterns and then work it down to less code so you can figure out what's going on. Any questions? Anything? Okay. Next slide. Well, last thing we're going to talk about today is memoization, which is dynamic programming if you've done 340, 374. So if you look at this Fibonacci program here, if you call fib 100, it's going to take a while. This is going to take a while because every fib call will run 2 more Fibonacci calls and then so on and so forth until we get to the bottom. So it's a very big recursion tree. It's going to take a long time to evaluate. So wait, before, if you've seen Fibonacci, I mean, you probably know that there's a closed form for this, and there's no reason to do this sort of recursion. But in the context of reverse engineering, the binary may have some function that is doing this, and you can't really rewrite it. So what can we do? Next slide. What we can do is we can save the inputs into a lookup table and then provide it to the function as needed. And this only works if the function has no side effects, so it doesn't like read anything from disk or from the internet or doesn't write to anything. If it's, I believe, idempotent or something. I don't know if that's the right term, but yeah, as long as it has no side effects and it returns the same output for the same input, then we can cache these values to speed up the execution a lot. Next slide. So a real world example, this is too inefficient from NightCTF 2021. This is a Ghidra snippet on the right here. And you don't have to look through the whole thing. The important thing is the 2 recursive calls in the middle of the function that get executed most of the time. And the disassembly or the decompilation looks pretty bad because this is written in Golang, and Ghidra is just suffering at this compiled Go. But what it's doing is it's computing n choose k using this recurrence above, and calling 2 copies of itself for each time that it runs. So just like the Fibonacci function that we saw before, this is going to take a long time. So what can we do about this? GDB Python to the rescue again. We can use GDB Python to hook into the calls as they. Oh, did something get cut off here? I don't know. Okay, no, we're all good. So we can use GDB Python to hook into the function calls and then replace the return value with the correct value. If it's already seen this particular call before, like if we called a function like choose for 1 and 1, then we don't need to run that again. We can just save that value and then use it over and over again. In this case, I just pre-computed all of the possible like n choose k values. I think they were doing I choose k for some fixed k and some I between 0 and the length of the flag. So I just computed that for every value and then stored into a file so that I can use GDB Python to put in the correct value exactly when needed without doing any computation. Yes, we have a question.
Sorry, can you go over how you do this? Like, are you basically just storing the value of like the predecessor there and then just using that and here with like changing it?
So the idea is that if the function, like in the general case, if the function has been called already with certain parameters, or sorry, once the function gets called with certain parameters, you can store that in like a hash table or a dictionary or something. And then if that function gets called again with the same parameters, you don't need to compute it. You just return, you just return the value. And GDB Python can do this with breakpoints. If we go to the next slide, just a full script example. If we break on the left arrow here, set a breakpoint at the function. The self.silent equals true is pretty important if you don't want your screen to explode with a bunch of messages. This will create a silent breakpoint in GDB Python. And then, yes, Nathan.
Which part of the script skips the function invocation?
Okay, so sorry, this is sort of a badish example because I ended up patching the original binary so that it would just do a return instead of computing anything. So if you look on the right here, it will set a breakpoint. It sets a break. So it sets a breakpoint on the left, and then on the right, once it hits the breakpoint, it will evaluate RAX, which is used for the input. Go has some weird calling conventions, but it looks that up on a table, and then I set RAX again for the return value, and then just let it continue. So yeah, so for this one, I did patch out the function. But what you could do in GDB Python is just manipulate the instruction pointers so that you skip the function entirely, if you know the cached values. Any other questions? Okay, we're almost done. Promise. Okay, yeah, this is go do challenges now. VMware 0 to 2. There's also Hell, which is another pretty gnarly reverse engineering challenge. Both of these are on the CTFD. And there's also obfuscated, which I did go over the solution, but I'd encourage you guys to just do it on your own because it's very rewarding. I'll promise you that. You can find that on the old YOU CTF website. So next slide, just next meetings this Sunday. Nathan will cover Nintendo DSi browser hacking. So be sure to come out to that. And then next Thursday, we'll have quantum computation with George. Yeah, that's all for this meeting. Thank you guys. I'll give you guys like a moment to look over VMware 0, and then I'll do a walkthrough of them. Give you guys like 10 minutes. Assembler.py on the, okay, so first of all, you run file on main, you can see that it's a x86 executable. And if you run file on prog, it's just random data because this is just random data. You'll run it through XXT. Does seem like there's some strings in there though. So I don't know. Maybe if you run strings, you can solve it. You can't, but something to keep in mind. Okay, so if I run main with prog, that's how you run the binary. It'll ask you for a password. Type something in, something in. Incorrect password. Oh no. So what do we do? So to run the disassembler, you can do disassembler prog. And this outputs a bunch of stuff. So this is like the instructions that were in the VM. That's sorry, not that are in the prog file that the disassembler is printing out for you. So you can look over these. They're pretty self-explanatory. You know, you got push, XOR, pop. And if you look at the source code, which I've graciously given you here today, you can see what each instruction does. So the opcodes are up here. And then we've got, this is like the big switch statement that interprets all of the opcodes. So yeah, think about how you might go about solving something like this. A lot of the hard work has been done already, getting the instructions. So now you just look at this. I mean, this is really sort of a simplified version of like x86 or something, except it uses the stack a lot and there's no registers. So I'll give you guys a moment to work on this and then do a walkthrough. No, sorry, there's no registers. There's registers in x86. There's no registers in this thing. Yeah, this VM that I've made. Yeah, go look at the challenge, guys. All right, guys, I'm gonna do a walkthrough of VMware 0 now. If you guys haven't been able to solve it already, don't worry. I'll show you how to do VMware 0, and then you guys can look at VMware 1 and 2. So first things first, we have, guys, let's focus, please. Write the program. It gives an incorrect password. And then let's look at the disassembly. So I'm going to disassemble the program and then just output it to a file just so we can look at it. If you look through this disassembly, some things jump out. I'm just scrolling through this. There does seem some, okay, so there does seem to be some sort of structure. There's like a bunch of pushes, a lot of numbers. Maybe this is the flag, who knows? And then some more numbers, and then a bunch of in commands, and then this sort of regular repeating section. This makes me very suspect because usually something repeating like this, it's doing possibly something related to the flag because got a lot of XORs. But I don't know. There's not much else to it if you look at the end. More pushes. So let's see if these are, maybe this is the flag. If you look at, okay, well, let's look at the raw binary. Oh, okay, so I know from writing the disassembler, but if you look through the disassembler, you'll see that the arguments are just stored directly in the, oh my God, this thing is so laggy. I'm sorry. The arguments are just stored directly in the binary as bytes. This line here, bytecode I+1, it just takes whatever byte is in there and it treats that as the argument to push. So given that, if we look at this assembly through hexdump, the program through hexdump, you'll see that these are all the pushes in the beginning. These are all the pushes. So 0A corresponds to the push instruction, which on this line, as you can see, it's 10. So these are all the pushes, and it just looks like to be pushing welcome to VMware 0, which is not very helpful. Where did my cursor go? This stuff. So all those pushes in the beginning probably aren't going to help us much. So, well, at least we know that. Now let's look at what's in the end. Oh, let's see. There's incorrect string and a correct string. So I'm guessing we'd have to somehow cause the program to print correct. I mean, that's probably a pretty valid assumption. So let's think about how we might do that. Now, normally at this point, I might generate a control flow graph of this. And you guys can do that if you want to, but it's sort of short enough that you can just look at it and reason about the execution. So we know from the XXD, the hexdump, that the last thing here, all these pushes are printing, or at least it's the string for incorrect. And then above that, this is the string for the correct output. So how do you get to this? Well, if I work my way up, you get this pop, jump, jump 0. These two instructions look pretty interesting. If it's 0, it's going to jump to 01C7, which is this big section where we're pushing. Remember, this is the correct string, the output where it says, oh, this is correct. And then if it's not 0, it's going to fall through to that jump, which jumps to 01E4. If you look at 01E4, that just comes down here to the incorrect string. So now that I have an idea that we need this to be 0, how might this be 0? Okay, so let's work our way up. So now there's a bunch of the stuff immediately before this is all this like repeating code, right? So we can break this down. So we have an XOR, a push, XOR push. So it's just XORing something twice, once with 106 and another time with 23. And if you look above, these numbers change. But look, 21, 22, 23, that seems to be incrementing. Interesting. Okay, so before the two XORs and pushes, we have a pop, a jump. Yeah, hard to tell what these are. But if you look, the jumps all go to, the jumps go to different locations. It's kind of confusing. So the thing in the parentheses is the address. So if it's 0, it's going to go to the next thing. And then if it's not 0, it's going to jump to 0 on E4, which again is this incorrect string that we saw earlier. So we don't want any of these to be 0, is essentially what these are all saying. So it's doing some pushes, some XORing. At this point, if you see this in a CTF, you can probably guess that it might be XORing this with the flag. I mean, what else would it be XORing with? So if you don't want to really guess that, we can look up here to the inputs. So the in instruction will push whatever byte you input onto the stack. If you look at main.c, you'll see that that is the case. And then there's a reverse, and then it jumps immediately to the XORs and pushes. So this is likely XORing this with the flag. So why don't we extract all these pushes and XORs and then do it on ourselves in Python. All right. Oh boy. I have enough time here. So I'm just going to copy this. Let's see. So so the only thing that we're pushing is things that it's XORing. So why don't I delete every line that's not a push? Okay. So I deleted every line that's not a push. These are the things that it's pushing it with. And we know that each byte, look at this assemble. So there's a jump 0 for every 2 pushes. 2 pushes and XORs. So there's a lot of guessing, I know, and part of that is sort of I'm just taking the shortcut here for this demonstration. But if you run this, just reason about the code some more. This push XOR, and then you're pushing XOR again. It leaves the stack the same except for the XORed result. So these are both operating on the same input byte, essentially. So each of these pushes, each pair of pushes gets applied to the same byte. So how do we do that with Python? Let's see. Okay, let me delete this. Write a macro. Okay, so now these are paired up. So turn these into XORs. So let's, oh, no. What did I do? Don't die on me. What? Oh my God. What? Oh no. No.
I think you just gotta leave it.
I gotta leave it?
Like it'll fix itself.
It'll fix itself.
It's a bit of a.
Oh my God.
I hate this story.
Okay, we're back. Share. All right. So back to here. Let's quickly. So I'm XORing these and then turning these into characters. You lost. Okay. Turning these into characters. Let's just see. This is probably not the easiest way to do it, but right. So these are all the commands. So I'm just gonna drop into a Python shell and then put these in. What the? Oh, it's guys, you didn't remind me of this. It's CHR. Okay. Oh my God. No. Okay. Well, good. I just can't like touch the computer. Kind of an issue. Okay. Python. Hey. Oh my God, that looks like the flag. Yo, so hype. Okay. Yeah. That's the demo. Thank you guys for listening. Um, yeah, I know there was a lot of guesswork there, but it's just in the interest of time. It's very hard to solve one of these like actually in 10 minutes, but yeah, did someone have a question? Yeah.
How can you learn seven of you?
You just use it a lot. Yeah. It's just yeah, it's really handy once you start using it. It's just so good, like replacing stuff. Yeah. Oh, so this CHR in Python converts a number to a character, or does the opposite thing, which I was using the wrong function earlier. Yeah, so we got from the disassembly that it's likely XORing the whatever your input is with two things, and then checking if that's zero. So two things exported is only zero if only if the two are equal. Only the two are equal. So I'm just XORing both of these. And then I know that that's going to get XORed to the flag. So yeah, that's why. Yeah.
So is it like input like they're like stuff on the stack, right? And then
Yes.
these numbers that are like hard coded in.
Yes.
That's like the actual flag that we XOR with the password, right? That we can type in.
Yes.
Oh.
Yeah.
Can you go back to your like secret that you had, like the XOR actual like line you had in Python. So on the left side, I think
Sorry, this caret is just Vim. Are you talking about the gray little blue?
Talking about like there's two numbers involved in XOR operation. So,
Yes.
left and right.
Yeah.
So what was them to the left, what was them to the right?
So there's actually three numbers here, if you think about it. The third number is your input flag, and it needs to be zero.
Oh.
And two of these numbers are hard-coded, right? The two that were given to us. And we know that the flag is the thing that we don't know. So if you just X with the other two, this will give us what the flag should be. Yeah.
Perhaps you could like just write one line of Python code that like you have a block of 5 VM instructions and that got converted into one.
Right. Yeah.
Can you just step through that?
Wait, say that again?
So like our input is popped off the stack. So that would be like the first input on.
Yeah. Or this is not actually, it's already on the stack. So XOR will operate on two elements on the stack. So this is
Yeah.
yeah.
So our input and 101 are on the stack.
Mm-hmm.
And then they get XORed.
Right.
And then the result of that and 2 get XORed.
Yes.
And then that output is 0.
Yeah.
Then all is good.
Yeah,
So
exactly.
sort of 2 and 101.
2
Yes.
101 and your input.
Two of those, yeah, 2 and 1, 101.
Yeah. So what we're getting at is like for the 0th character, we're XORing 115, 0, and then flag 0, the 0th character. Right. So in this case, this whole thing needs to be equal to 0 due to the jump 0 that we saw, like for example, on B0 line. Okay. This whole thing needs to be 0. And then we know 2 of these already. We know that 1, 1, 5, and 0. So if we just, this is like a property of XOR, but you can just XOR these again on the right side. Oh, fuck. On the right side. And then the left side gets canceled out. So the flag becomes equal to the right-hand side here. So that's what we're doing is we're just XORing 0. And 0 is a identity when XORing. So this just becomes 115 XOR with 0. Yeah. Good question. I did skip a lot of steps just because it's very hard to do a walkthrough like this because these challenges you have to keep in mind are already like some of the hardest rev that you'll see. That's why this is rev 3. So I've tried my best to distill it down to its essence, have a simpler example. But even then, it's pretty involved, as you can see. Yeah. Thank you.